Hey guys, we're continuing our discussion of linear regression in Chapter 8. We're building off of what we did in Chapter 7 where we created a correlation coefficient, which we called R. And I kind of hinted to what this was at the end of Chapter 7 because we actually went through and calculated a line of best fit. And our line of best fit, or our linear regression model, or our regression line, those are all things that we're going to use in order to eventually hopefully make good predictions based off of the data that we have. And so what we're going to learn in this particular unit is how to come up with that line of best fit. And we're going to use the calculator for that. And we are going to, of course, learn some more vocabulary and be able to interpret what we see in the calculator, and then eventually also be able to interpret what we see when we don't have a calculator, but we have a computer program, which most of you guys, when you go off to school and you take other courses involving statistics, you'll have different programs. There's Minitab, there's ActiveStats, there's all kinds of different programs, but they all pretty much spit out the same information. We just got to know how to read that information and interpret it. So we're going to talk about this line of best fit, and the good news is we link this line of best fit up with what you guys have done in Algebra and Algebra 2 because it has a slope, it has a y-intercept, and so you guys already know how to interpret those, hopefully. Just because this is a weird math class, it's still a math class, so those things still mean the same thing that they always have to you. And then finally, we take a look and say, well, how good are our predictions? How good are we going to feel about making our predictions? And we evaluate that using R squared, which is the thing that we didn't get to talk about in Chapter 7. All right, so here we go. The regression line, like I said, is also called the line of best fit. You also see it referred to as the linear model, but it's a straight line that supports a prediction. Okay, so we're going to try to make a prediction of a dependent response variable, y. So we're going to try to predict y based off a given independent explanatory variable, x. And the way that we do this is we measure error, the difference between what actually happens and what we predict to happen. Now, as I said in the last chapter, be careful. We use dependent and independent just so you guys can be, link it up with what you've done in science before and what you've done in math before. But remember this, looking at a scatter plot, we cannot jump to the conclusion that one thing causes the other. So don't assume causation just because we use the word dependent. All right, first definition is a residual. And a residual is a difference between an observed y and a predicted y. So that's our error, okay? It's what's left over. So I always think residue, like when you wash the dishes and you drain the water and you got the soap residue or whatever, it's what's left over. So a residual is, I call it Marie Hidalgo's rule. She's one of my students in my first years of teaching stats, and she came up with this, and she said, how do you remember how to get the residual? She said, well, I'm in an AP class, and so actual minus predicted is how you get a residual. And what we mean by that is that these dots right here, those are our scatter plot. That is our actual data, okay? So, I mean, we don't have a scale, but let's say that this is x is equal to 1 and y is equal to 6 or something like that. So when x is equal to 1, y is equal to 6. This is what actually happens when x is equal to 1. But if I use this line of best fit, this prediction line, this regression line, then I would predict that y would be something right here, half of that, maybe 3 or 3.5-ish, something like that. That is my predicted. So actual minus predicted, when the actual is above the predicted line, actual minus predicted is going to be a positive number, right? And so if you have a positive residual, then that means you have an underestimate, meaning that we're going to use this line right here, hopefully, after we determine some other things. If it's a good line to use, we're going to use this line to make predictions. And so if I predict what happens at x equals 1 using this line, I'm predicting a number that's smaller than what actually happens. And so therefore, when you have a positive residual, when this number right here minus this number is positive, then we are underestimating when we use our line of best fit in order to make a prediction. But on the flip side, when x is equal to 3, this is what actually happened. I don't know, maybe 2 or something like that. And then what we would predict to happen would be 4 or something like that, you know? So again, when you do actual 2 minus predicted 4, then you're going to get a negative number. So whenever you get a negative residual, then you have overestimated what actually happened when x was equal to 3. All right, and so instead of having to memorize this and going, okay, it's the opposite of what I think, negative, over and positive under, just sketch this real quick and think it through and think of Marie Hidalgo's rule, AP, A minus P, actual minus predicted. You're in an AP class. All right, now this line of best fit is the line that's designed to minimize. I know this looks scary at first, but let's just think through it. This right here is sigma. It means the sum of, and this is what actually happened minus what we call this y hat. That little caret right there is y hat, just like p hat, and it's what we would predict to happen. And then if you square that, so it's the sum of the squared differences between what is actually happening and what we predict to happen. So in other words, or instead of symbols in words, it is the sum of the squares of the residuals. And so the calculator is going to do all this stuff for us, but what is it really doing in the background? Here's a visual of kind of what it's doing. It's going like this and saying, okay, the actual minus the predicted. So it takes the difference between here and here, and it creates a square. Okay, so the square, you guys know all the sides of a square are the same. So if I square, do length times width or side times side, don't you get the area of the square? And so what the calculator is trying to do when it creates a line of best fit in the background, it's not trying to hit as many points as possible. That's not what it does. It's trying to move through the middle-ish of as many points as possible. But another way of thinking about that is it's going in the background and figuring out what these squares are, what the areas are of these squares. And what it wants to do is it wants to limit that. So it wants the sum of the squares of the residuals to be as small as possible. So it wants these areas, when you add them all up, to be as small as possible when you add all of the data up. So that's kind of what it's doing in the background to give you a visual of what's going on, okay? So important facts about the least squares regression model. So our linear model, our line of best fit, again, I'm just going to keep on saying that over and over again so you know it's all the same thing, is of course we don't want to create a scatter plot unless we have quantitative variables. So if we're doing a line of best fit through a scatter plot, then of course we don't want to do a line of best fit unless our data is both categorical variables. I'm sorry, quantitative variables. If I say categorical before, I'm sorry, it's quantitative variables. And then, like I said before, we want to make sure that our scatter plot looks reasonably straight. Again, it's not going to be on an exact straight line. That's very rare that that happens. But we say it's, it's somewhat linear. It's not curved. It's not exponential curve or look like a parabola or something like that. And then, as we said, for outliers, we want to make sure that we don't need to pay attention to some weird looking points that don't fit the overall pattern. Okay, so last chapter we said correlation R, which the full name for it is the correlation coefficient. R ignores the distinction between explanatory and response variables. Remember, R doesn't care what your units are. R doesn't care which one is X and which one is Y. Okay, you can move those back and forth, switch those, and R will still be the same. Okay, as correlation grows less strong, so correlation, as your R grows closer to 0, remember if it gets close to 1 or -1, it's strong, but as it gets closer to 0, so as it grows less strong, the prediction y hat will move less in response to changes in X. Okay, so that's why we want our R to be pretty high. We want it to be strong. We don't want it to be close to 0 because then our predictions that we're going to make, we don't really trust them all that much. All right, but so R doesn't care about units. R doesn't care which one your explanatory and response variable is. But when you run regression, so when you create a line of best fit, you must know which one is the explanatory and which one is the response. And it's based off of what I was just showing you guys visually. Regression measures the distance between in the y direction. And so if you change your x and your y values, If you flip-flop those, as you guys hopefully know from previous math classes, when you find the inverse, you get a different looking line, right? A different looking equation. And so it's the same thing that's going to happen here. If we change our x and our y, R still ain't going to care, but our regression line will be different. So it's important to make sure we know what are we trying to predict, and what information do we have. So you got to pay attention to that. All right. Now here's some things that are that you need to know, and you will have to use this. These are the type of things that they'll put in a problem, without coming out and saying, hey, you need to know this. So these are the things that you want to know, characteristics again about the line of best fit that you want to know so you can answer other questions. The point x bar, y bar will always be on the line of best fit. Okay, so x bar is just the average of all the x values, y bar is the average of all the y values. And now make sure that you understand what you're writing down there. I did not say that x bar, y bar will be a point on your scatter plot. That's not what I said. I said the point x bar, y bar will be on your line of best fit always. Okay, so that's something that's good to know. You'll use that in order to answer some questions, by knowing that simple fact right there. The form of our line of best fit, y hat, we read that just like we read p hat. Y hat, that's our predicted value, is a plus bx. We saw that when I told you how to run regression in the calculator in chapter 7. We're going to use number 8, StatCalc 8 instead of StatCalc 4. So the version that we use in stats is a plus bx, where a is our y-intercept, because that's your constant. That's the thing that's all but, it's the number that's going to be all by itself. And then b is your coefficient of your independent variable. So the coefficient of my x-axis, my x variable, that is going to be our slope, right? So that might take a little bit of getting used to at first because we thought of it the other way in Algebra 2. All right, now the slope, how can you figure out what this slope number is? Well, there's going to be different ways of doing that, but remember we said that the slope is based off of standardized values. So this formula right here is how we're going to get the slope sometimes. We'll need, they'll give us some other information, and then we can use that information in order to calculate the slope. So all we're going to do is take our correlation coefficient, multiply it times the standard deviation of y over the standard deviation of our x data. Now it's important that you know it has to be y over x. It shouldn't be too hard because the slope that you guys have always known is rise over run, and so you always put your y's on top. The difference in your y's on top, the difference in your x's on the bottom. Now, again, the great thing about stats is you don't have to memorize this formula, because if you pull up your formula sheet and you look on the first page in section 1 right here, it tells you what that formula is, so you don't have to try to do that by memory and accidentally screw that up by putting your standard deviation of x over standard deviation of y. It's on the formula sheet for you. Don't waste that pretty precious brain space trying to memorize formulas and stats. It's all on the formula sheet. Just know where to go get it. All right, and so what is your slope though? Like I said, this is the same thing as it was in Algebra 2. It's the estimated unit rate change of the response variable per unit change of the explanatory variable. So you learned it in algebra as the change in y with respect to the change of x. Okay, so as x increases by 1, how much does y change? That sort of thing. It's still the same mathematical thing, slope. All right. Now our y-intercept, if I take this equation that we just talked about, y hat equals a plus bx, and I just do algebra on it to get a by itself, then I get a is equal to y bar minus b times x bar. Now the reason why I'm using y bar and x bar is because I know that that point has to be on this line. Okay, so that is the y-intercept, and as I said before, this is the same thing as it always has been. The y-intercept is when you're on the y-axis, and you're only on the y-axis when your explanatory variable or your x variable is equal to 0. And that's the same thing. So it's what's the y value when the value of x is 0? Same thing as it always has been. Okay, interpolating. Here's another vocabulary word. When we use the equation to predict a y value for an x value that's within our x data set. All right, So if, for instance, if my old job, I worked at Ferguson, I was in sales, and so if I had all my sales records or my sales numbers from January to December, and I had all of those numbers except for October. So I know that month one, January, I had a certain amount of sales. Month two, February, I had a certain amount of sales, all the way up through to 12. But in October, for some reason, I didn't write those down. If I wanted to use a line of best fit in order to predict what happened within my data, so from 1 to 12, number 10, I would know that. Then that would be interpolating because I'm trying to make a prediction within the values that I have. Now, if I go through that first year of sales and then I try to predict what's going to happen in the months in the future that have not happened yet, then I call that extrapolating. So when we use the equation to predict a y value that's for an x value that's outside of the data that we already have. And we'll see a couple of situations like that. And that's commonly used. Extrapolating, we create a model based off of what's happened in the past, and then we try to predict what's going to happen in the future. And that's okay as long as we don't go too far out in advance, because things can happen like a pandemic or and shut down construction or whatever. Or so we don't want to go too far out. We don't want to extrapolate too far out, but people do it all the time to try to make a prediction as what's going to happen in the future so they can make better decisions. All right, so let's get this straight. We just said that B is the slope of the line of best fit. Okay, we had a formula to calculate that. We also said that R is the slope of the line if we had standardized, so turned all of our X values and all of our Y values into Z-scores for each one of those variables, X's and Y's. Because of this, we need to keep in mind that moving any number of standard deviations in the X direction will move R times that number of standard deviations in the Y direction. So remember, Y is based off of where Y is based off of X most of the time, right? So, but it's not totally based off of that. So I know that definition right there, that scenario seems kind of weird. So I figured I'd show you a couple of problems so you could just get the idea, okay? Because sometimes, like in all math classes, if we put the gobbledygook theorems down and all that stuff in general, X's and Y's, it doesn't make sense. But if you use actual numbers, then it does. So here you go to try to understand what I mean by this slide right here. If we had a scatter plot of house prices that were in thousands of dollars versus house size in thousands of square feet, and it shows a relationship that is straight, so with only moderate scatter and no outliers. So that's just saying it's relatively straight. So therefore, it's okay. Those are both quantitative variables. And we get a correlation between house price and house size as 0.85. And that's a strong relationship, right? Because it's close to 1. And so you're looking at this and you're like, well, which one of these is my Y variable or my response variable, and which one is my X variable? Well, the bigger the house is, more likely the bigger the price is going to be, right? So the house price is probably our response variable, our Y variable, and house size is going to be our X variable. So if I say a house is 1 standard deviations above the mean in size, so in the X direction, 1 standard deviation above the average, how many standard deviations above the mean would you predict its sales price to be? So what do you think would happen to its Y value? And so we know that if our R is 0.85, we know that we're going to say that for each standard deviation move in X, the standard deviation in Y is going to move 0.85. So we would say it would be about 0.85 standard deviations above the mean price, because this is above the mean size, so we're going to go above the mean price. All right, or another example, what would you predict about the sales price of a house that's 2 standard deviations below an average size? Well, if it's 2 standard deviations below an average size, then that means its price is going to be 2 standard deviations below a mean price. So, but it's going to be 2 standard deviations times R. So we would say 1.7 standard deviations below the mean price. So you probably won't see too many questions like that, but just in case you did, it's important to know that so you can get that multiple choice question right pretty easy. All right, and then again, like I said in the last chapter, we talked about R, which is called the correlation coefficient. R tells us the strength of our linear association between two quantitative variables. But then when we ran regression, we also, if we turned our stats diagnostics on, we also got an R squared value. Well, as you can imagine, if you take R and you square it, you're going to get R squared. But we call R squared the coefficient of determination. Now, this is kind of weird because R is called the correlation coefficient, and then R squared is the coefficient of determination. The way I keep it straight in my head is I think R before I think R squared, and then I think alphabetically R, and then or alphabetically correlation coefficient CC, correlation coefficient comes first, and then CD, D comes after C, so CD goes with the R squared, so the coefficient of determination. And that's important to make sure that you have the distinction between those two, because when you're reading a problem, they tell you to report the coefficient of determination. You don't want to report R. You want to make sure that you know that they're asking about R squared. So please, somehow jot that down and make a note of that so you understand that there is a difference between R and R squared. They are related, because how do I get to R if I have R squared? Take the square root. How do I get to R squared if I have R? Square it. But what it does is it provides information regarding the percent of the variation in the values of y that can be explained by the least squares regression line of y on x. So it's basically telling us how much does y depend on, or how much does where y is, how much does that depend on where x is with our model. And so this is one of those things, we've said several units or several objectives that we've talked about throughout the year. You have to say it a certain way, like when you're describing a p-value, when you're describing a confidence interval, when when you talk about a simulation, you say according to this model, that sort of thing. So here's another one of those cases. How do I interpret R squared? So if the R squared between the independent variable height and the dependent variable weight is 0.83. So again, independent variable, that would be our x-axis. The dependent variable would be our y-axis. If that R squared value is 0.83, then this is what we say. This is how we interpret R squared. We say that we can conclude that 83% of the variation in our y variable, we're going to have to put it in context to get full credit though. So my y variable, I'm going to say 83% of the variation in weight can be accounted for, or you'll also see can be explained by my x variable. So height in context of the problem, by height according to this model. This right here, this sentence right here, or from right here, 80, we can conclude, this part of the sentence, we can conclude that 83% of the variation in weight can be accounted for by height according to this model. That's what you need minimum to describe what R squared, or to interpret what R squared is telling us. Well, if 83% can be explained by what x is, so by what height is, then that means 17% of how weight moves, how weight varies, must be attributed to something other than just your height. Okay, and we've talked about that before. It all depends on other things, metabolism and genes, and what you eat and all that good stuff too. So it's not just your height that explains all of your weight. It's a big factor, but it doesn't explain all of your weight, right? So that's what we're talking about there, R squared. And so if R squared is pretty high, then we're going to feel good about making these predictions. All right, so other things to note, the sum of the deviations from the mean is 0. Okay, the sum of our residuals. So remember, residuals are actual minus predicted, or the errors. And so we're going to get some positive residuals. We're going to get some negative residuals. The calculator tries to make sure that that sum is 0. When you add up all the positive residuals and the negative residuals, you're going to get 0. Be careful here, R squared, sometimes our data will report, or a problem will report, that R squared is greater than 0. And think about it, when you calculate something in your calculator, you're always going to get a positive number for R squared, right? because when you square something, you get positive numbers. That's just plain mathy math, right? But just be careful, because if they give you r squared and you have to work your way back down to r, I told you before we're going to take the square root of r squared to get down to r. But you guys know that when you decide to take the square root, you got to think, well, it's either positive or negative, right? The square root of 49 is actually plus or minus 7. So when they report the r squared and you're trying to figure out what r is for some reason, don't automatically assume that r has to be positive as well, because this number is always going to be positive. So if x and y are negatively associated, then we know that r has to be less than 0. So for instance, this right here is a strong positive associated scatter plot, right? A relationship between two quantitative variables. And so r squared is going to be positive, but when you take the square root of it, you're going to get a positive r, because a line that has a positive slope will go through this. But back here, for this particular data set, you'll get the same exact r squared for this picture as you do for this picture. Okay, but we know that this is a negative association, so if it's a negative association, then that means r has to be less than 0. So just be careful with that. They try to trick you with that, so don't be that guy. All right, our least squares regression model is only good for making predictions when the scatter plot of the data appears to be linear. Okay, so remember we talked about how you have to have two quantitative variables, and then we said that your data has to be, somewhat linear, right? And I told you up until this particular chapter, you were just going to use your eyes in order to determine whether you think it's straight or not, whether we have a good model. Okay, so again, how can we tell if we're using a good model? Meaning, how can we tell if our line of best fit should be used to make predictions? Well, it's got to be linear. If our data is not linear, then we should not be using r, and we should not be talking about r squared and any of this stuff. It doesn't make sense. Okay, so how do we do this without just relying on our eyes? Well, we create a residual plot. All right, our residual plot will display the scatter plot of the points x, so it's still saying my normal x values in my data, and we're plotting those against y minus y hat, which those are our residuals. So basically what we're doing is we're saying, how big of an error do we have when x is equal to 1? How big of an error do we have when x is equal to 2? And so we're plotting that those errors, those residuals, against our x values. So we're saying what is the error at each one of those spots. And that's called a residual plot. Now, the mean of the residuals is always going to be equal to 0. And here is the big thing. You will definitely have a question about this either on the multiple choice or free response of the AP exam. I guarantee it. If there is a definite pattern in your residual plot, then a linear model is not a good fit for our data. So this is going to be the determination, how we figure out whether or not we should use our line of best fit, is looking at our residual plot. So what I mean by that is sometimes you might get data that is curved in your residual plot. Again, this is a different plot than what your original scatter plot looks like. So remember back when we were talking about normal probability plots, and I told you have to be specific and name what it is that we're looking at, because normal probability plots, scatter plots, and residual plots, if you don't know what they are, they all kind of look like the same thing. So we've got to make sure that we label these things. But if you do a residual plot, which I'm going to show you how to do that in the calculator in a few minutes, and you get something that looks, I don't know, something that looks kind of like that, that's a curve, okay? And so if you see something that looks like that, that is a pattern in your residual plot, and we would say, all right, if I see that in my residual plot, I don't want to use this line of best fit to make predictions, because my data is not linear. And if my data is not linear, then that means R doesn't really make any sense either. So as we talked about in chapter 7. Another thing that you might see is unbalanced, okay? And so what I mean by that is if we have, whoops, um, so something like this, to where you see how we have a lot of positive residuals and only a few negative residuals. So that means that if we use this model in order to make predictions, most of the time we have residuals that are positive. And if you remember back to the beginning of the presentation, positive residuals means that we would be underestimating. So if you saw something that looked like this, our line of best fit would underestimate most of the time, and that's not good. So we wouldn't want to use that. Uh, we wouldn't want to use a linear model if we see this in our residual plot. Or the other thing, megaphone shaped, and it's not going to be as pronounced as this, but I'm going to draw it that way just so you can see why we call it a megaphone. If you like this and drew that, and you got somebody right here yelling, "Hey, cheerleader," whatever. Okay, so that's too much stuff, right? But anyways, if you see a pattern that looks like this, to where as you're moving out, the residuals are getting bigger and bigger and bigger. And if the residuals are getting bigger as x gets bigger, something like this, then that means that this model will be good when x is small. So you're making good predictions. You got some positive, some negative, so that's good. But as x gets further and further, or bigger and bigger, then our residuals start getting lots bigger. And if that's the case, then that means that we're not making good predictions as x gets bigger. So going back to an example that I talked about earlier, trying to estimate sales throughout the year, you'll be making good predictions January, February, and March, but then they start to get not so good in April, and then by the time you get to December, your predictions are going to be way off. So you wouldn't want to use a line of best fit that would create a residual plot that looks like that. Okay, so if you see a pattern in your residual plot, your data is not linear. All right, and so finally, let's go through a couple examples so I can show you guys how the calculator is going to create these numbers for us, and then so we can practice a couple of times interpreting some things. Okay, so the data shown represents the number of books and the depth of paper in inches on 10 college students' desks at a randomly chosen time. So here we got number of books, here we got inches of paper. And so before you start typing stuff into the calculator, again, try to think which one do you think would be the explanatory variable and which one do you think would be the response, because it's not always the first thing that you see is the explanatory. Hopefully it would be, but we got to think before we just start punching buttons, right? And so hopefully you guys kind of think, right? And the more books you have, then the more classes you're taking, meaning the more inches of paper you're going to have because you got more work to do, right? So anyways, this does appear to be the explanatory variable, the x variable, and this appears to be the response variable, the y variable. So what I want to do is to create a scatter plot first from that data. And let's see here, I can get my calculator to pop up here. Got too many things open. There we go. So go into your calculator and do your statistical plot. So remember, we're going to go stat and then edit. And so in list 1 and in list 2, we're going to put list 1, we're going to put our number of books. And in list 2, we're going to put our inches of paper on our desk. You don't need this other stuff over here yet, so don't worry about that. I thought I had done something. All right, so so we got that taken care of. Pause and that good stuff. So now I'm going to do a scatter plot. So second y equals, we're turning our scatter plot on, and then we pick this one for our type. We've got our stuff in our X list as L1, and L2 is the stuff from our Y list, and then we just hit zoom 9 like that, and then we get a scatter plot. Okay, so again, just using our eyes based off of chapter 7 stuff, we look at this, we say, okay, how would you describe this association? I would say that there is a positive association, meaning that as x increases, y tends to increase. I would say that it was probably moderate, okay? because these are not real close together, but there seems to be a pretty good line. This looks like linear data, right? So I would say linear based off of my eyes. I would say that this is linear data. Okay, so we've got our scatter plot. Then the next thing I want you guys to do is, in order to get our residuals, because we need to draw a residual plot. In order to get a residual plot, we need to calculate our residuals. Residuals are the difference between, okay, if I draw a line up in between this stuff, a line of best fit, there's going to be actual value minus predicted values. And so we've got to get the calculator to create those residuals before we can get it to give us a residual plot. So the calculator needs to have a line of best fit so it can figure out what it's going to use for the prediction part of a residual, actual minus predicted. So what we want to do is we want to run regression. So remember, we're going to go stat, we're going to go over to calc, we're going to choose number 8, and I got my stuff in list 1 and list 2. I'm going to bounce down to my regression equation. Where do I want to store my regression equation? I want to put that in y1. So we hit vars, we go to the right to y vars, and then we push enter, enter, because we want the function to go into y1. And then when you hit calculate, the calculator is doing lots of stuff here. It's calculating our least squares regression line. Remember what we said at the beginning of the presentation. It's making sure that those boxes are as small as possible when you add them all up. And so it's created our line of best fit here, where A is our constant, which is our y-intercept, and B is our slope. So 0.8031. It gives us our coefficient of determination, r squared, and it gives us our correlation coefficient, which is r. And so when you see r is equal to 0.62, then right there you're like, okay, cool. I said it was moderate, 0.62. That's okay. If you said moderately strong, maybe, yeah, because it's bigger than 0.5, that'd be fine. But that was based off of our eyes only. And so this seems like it's going to be a good number to use to describe our association. But let's make sure by looking at our residual plot. Now first, I want to just give you guys the visual. When you go to y equals, it takes that equation that it was just broke down for you, told you what A was, told you what B is. It takes that equation and it puts it in y1 for you. That way, when you hit zoom 9 now and you look at your scatter plot, you have your line of best fit that's going through there as well. Okay, and so when you run your regression and you put it into L1, then the calculator has everything it needs to calculate the difference between this, what actually happened, and what it's predicting to happen at that particular moment. And so what we're going to do is to draw our residual plot. Okay, so remember this is our scatter plot with a line of best fit going through it. Now what we want to do is draw our residual plot. So if you go into second y equals, if you go back to your stat plot, and now the only thing that you have to do is remember our residual plot still involves our x values, but then our y values are going to be the residuals. Well, what's cool right here is if you look above your stat button, it says list. So if you hit second and then the stat button, if you have done the process of running regression and putting it into y1, then this down here, resid list, will show up when you hit second stat. It'll show up a list called residual because the calculator has an equation in it in y1 to where it can do the actual minus predicted. If you get to this step and you don't see resid down here, then that means you forgot to run regression first. And the calculator can't give you the residuals because it doesn't have anything to work. It doesn't just make up numbers. All right, so if I pick 7 as residuals to be my Y list, now when I hit zoom 9, okay, you see this is still our line of best fit, and that's going to still show up unless you go to Y equals and pause that for a second. So just kind of ignore that line right now. But it is nice to still have it there so you guys can see that this is clearly different than the scatter plot. And so when you're looking at this, you've got to decide, do you see a particular pattern here Does it look like it's curved? Does it look like it's exponential curve? Try to check the balance thing. We've got, and when I say balance, that doesn't mean it has to be the exact same amount of positive residuals as there are negative. It just has to be close to it. That's going to be kind of hard sometimes with our examples because we don't have a bunch of data to look at. We're only looking at small numbers of data, so that one kind of gets a little tricky at first, but um, I don't see a megaphone shape here. I don't see a curve. And so this looks pretty much scattered about. And so because of that, I'm able to say, all right, well, this data is in fact linear. So therefore, my R and my R squared, they mean something. All right, so that's the process on how to get a residual plot. And so this right here is what we're going to use. We're not going to use our eyes anymore and say it's somewhat linear. We're going to do a residual plot and make sure there's no pattern in our residual plot. And then that's what tells us, okay, our data is linear, so therefore it's cool to go ahead and create this line of best fit. And I'm going to use this line of best fit in order to make predictions. Now, even though it's legit cool, I'm going to do this real quick one more time. Stat calc 8. And then and get those numbers. So what we just figured out is that it is cool to go ahead and use this line of best fit to make predictions because we have determined that there's no pattern in our residual plot, so therefore our data is in fact linear. And if our data is in fact linear, then R makes sense here. Because remember, R only makes sense if you have linear data. It only measures the strength of linear association between two quantitative variables. So you're looking at this and you go, okay, well, this association is moderate to strong with a 0.62, but then we take a look at this R squared value, our coefficient of determination, and we go, well, how much of the variation in Y can be explained by X using this model? Even though it's legit, it's okay to use a linear model for this data because it is linear. How good are we going to feel about our predictions made is what we look at R squared, our coefficient of determination. And since that's only 38.5%, that's saying that 38.5, Y doesn't really depend on X all that much. How it moves, it does not depend on X all that much. So I can still make predictions, mathematically, I'm still legit making predictions using this line of best fit, but I'm not going to feel really strong about it. I'm not going to like put a bunch of money on that. Okay. So that's what we got going on there. And so then if we continue on with our notes, then we're going to do another problem. And so you guys see that in list 3 and list 4, I went on and we're going to talk about height and weight. So height and weight, I put those in list 3, height, and then I put weight as my Y list. Again, I think that height, somewhat can probably explain a little bit about how much you weigh. And so this is my response variable. So you guys can either go ahead and put them back in list 1 and list 2. Clear out what you got in list 1 and list 2. Remember to clear, you go to the top of the list. So not here, but bounce up one more to L1 and hit clear. Don't hit delete. And you can put in this data if you want to, or I'm just going to leave it in L3 and L4, and I'll show you what I'm going to do different, just in case you guys get into the same spot where you don't want to get rid of this data in case you might need it for later. All right, so part 1 says construct a scatter plot and describe its shape. So what I like to do is I like to go back into Y equals real quick and hit clear, because that line of best fit is going towards that old data. So I don't want to accidentally mix up and use that line of best fit for this new data. So I like to start with a clean slate. So I go and I do that, and I can quit. And then now what I want to do is I want to create a scatter plot. So second Y equals, and I have to come back down here. Now my data that I'm using for me is in list 3 as my X list, and then it's list 4 as my Y list. Okay, but if you guys put it back in L1 and L2, keep it and change it back to L1 and L2. So you can put it wherever you want to. You just, when you go to make this stuff, you got to make sure that the calculator knows what you want it to plot. And so if I hit zoom 9 here, I'm going to get that relationship. And so describe what it is that you see. Okay. All right. So if you do a scatter plot correctly, then you should see something that looks like this. Again, if you had to, jot this down as an answer, you'd want to label it the scatter plot, label your x and y axis. Okay, so height is x, weight is y, and we've got that right there. It says find the least squares regression line. So find the correlation coefficient and the coefficient of determination. So you guys know that you would have to run regression on that. And so you're going to do stat calc 8. And, again, wherever, make sure that you tell it where your data is. And then you want to put your regression equation into y1. And so if you do that, oops, yeah, sorry, it says describe this. We would say that this is strong. We would say it's positive because as x increases, y tends to increase, or it looks like a positive slope line would go through there. So we'd say positive, and it is linear. Of course, that's a pretty strong, that looks like a pretty strong relationship right there. So if we find our least squares regression line, then hopefully you guys got y hat is equal to negative 52.5 plus 3.04x. All right, and then our r value is 0.968. And our r squared is 0.937. So that's pretty good because r is telling us right now, if our data is in fact linear, which we're pretty sure, just by looking at with your eyes, you're pretty sure that that data is linear. But we're going to double check it with the residual plot. We're not going to just rely on our eyes anymore from here on out. So, but our least squares regression analysis gives us r as being 0.968, so that verifies us saying that it's a strong relationship, and then r squared is 0.937. So question 3 says interpret the slope and the coefficient of determination. So again, this is where there's one of those things where they tell you to interpret the slope. You're like, okay, well, which one is the slope? It's the coefficient of x. All right, and so 3.04 is our slope. And so remember, think back to algebra time. What is slope in algebra? The change in y with respect to x. How much does y change as x changes by 1 unit? That you can just start off that way to make it simpler. And then coefficient of determination, well, which one? Are you talking about this one or are you talking about this one? You have to make sure you know correlation coefficient is r and coefficient of determination is r squared. So how do you interpret those two things? The slope for each additional inch in height. So as x increases by 1 unit. So in our case, we'd say additional inch in height. As inch increases by 1, as height increases by 1 inch, then weight, notice that I say should, because remember, I don't want to say that one thing causes another based off of just a scatter plot. So I use words like should or tends to, right? Weight should increase by how much? 3.04, my slope. That's how you interpret the slope. And then r squared, go back to what we talked about. How do I determine, or how do I interpret coefficient of determination? How do I say r squared? It's going to be the same way every single time. You just have to change the context of the problem. Okay, so I'm going to say 93.7 to turn this into a percentage of variation in weight can be explained by height according to this model. According to this model is important because it's just based off of this data that we've got. Right? This is not all the data in the world. This is just one set of data. So this line of best fit comes from just this set of data. So this interpretation just works according to this model. We would say 93.7% of variation in weight can be explained by height according to that model. Okay. Number 4 says calculate the residuals and construct the residual plot. So again, what you can do is you can, if you've got your data in list 1 and in list 2, whoops, what you can do is you can go to list 3, go to the top of list 3. So again, highlight where it says list 3, and then just tell it to put the residuals there. So again, what you can do is just hit second stat, because above the stat key it says list, and then your residual should pop up again if you've ran your regression, which we did. That's the only way you could have gotten that equation that we had for answer number 2. So you can hit residual and it'll tell you what all of these residuals are. Okay, when x is equal to 48, what's the residual? What's the actual minus predicted? When x is equal to 50, so forth, right? It tells you all of those residuals. So if a question asked you to figure out what the residual was at a particular spot, you could do that real quick. You find them at all of them. Okay, practice getting the residual plot. And so if you go back up and you change, you go to second stat or second y equals, and you mess with your stat plot and change your y values to residual, then we get a residual plot that looks like this. Okay, and again, it's kind of weird because we only have 7 pieces of data, so you got 4 on the bottom, 4 and 3 on the top, but you don't go, oh, there's more on the bottom than there's on the top, so I can't use this. But I don't really see like a super curve or anything going on here. Maybe you might have an argument for this being parabolic, but it's just, again, because there's only 7 pieces of data. There's one piece right here. I'm not sure that this is really a curve, as much of it just being scattered about. So because you have no pattern in your residual plot, you would say, okay, our data is in fact linear. And so the other things that you can do sometimes when you are talking about your residuals, what else is this good for? They might say, hey, we'll take a look at 74, 180, okay? Because 180 seems like it's way different than 135 and all those things. And 74 is bigger than those, but only by 10, right? But so is 180, is that a possible outlier? Well, again, if you hit your trace button like we did in chapter 17 or 7, if you hit your trace button, you can bounce through all of these residuals so you can figure out which one is 74, 180, or you can just look back at your list right here and go 74, 180 and see that it has a residual of 7.6. That's a positive residual, so that means your prediction line that you would use to make predictions, our least squares regression line, our model, our line of best fit, when that residual is positive, we know we'd be underestimating. But check it out. You can bounce through by hitting trace and bouncing through each one of these points. You can show that right there. And just look, does the difference between here and the x-axis, does it look like it's all that much different than these other guys? Yeah, these guys right here, but not so much these, right? And you can take a look at the actual numbers up here and see that 7.6 is really not that much bigger of a residual than 6.3 and 5.5. So it's probably not a big deal. Another thing that you can do is you can go back to your stat plot, second y equals, and you can go back and take a look at your original scatter plot. And if you look at your original scatter plot, even though this point is way far away from all these guys in the x direction and in the y direction, doesn't it fit the overall pattern though? Our line of best fit goes through all these guys and goes through here, so you're looking at that difference right there. Not so, that is not even as big of a residual. It doesn't seem like as some of these other guys. I told you at the beginning of chapter 7 that an outlier in a scatter plot is something that doesn't look like it fits the overall pattern. So even though this point right here is far away from this point and these points in the x direction, and it's far away in the y direction, it's not an outlier because it fits this overall pattern. Okay, it's still close to that line as we go through. So we wouldn't say 74, 180 is an outlier. Discuss the goodness of fit of this model. They're just telling you, okay, all right, now that all of this analysis is done, what did you find out? What did all these numbers tell us? And so when they ask you to discuss the goodness of fit, then that they're asking you, okay, well, is this data linear? Well, how do you determine if it's linear or not? Is look at the residual plot. And so I said there does not appear to be an obvious curvature or a pattern in the residual plot. So that makes my data linear. So that means it's okay to talk about R and R squared. And so R told us that we, 0.968, that we had a strong association. And then now what I'm going to do is I'm going to talk about R squared, my coefficient of determination. And that number is high, 93.7%. Okay. So you can, what we wrote down in number 3 would be good for this answer as well if they didn't already prompt us to describe what or interpret what the coefficient of determination was previously. We'd probably want to go ahead and say, well, what does this 93.7 mean? And so because of that combination that my data is in fact linear since there's no pattern in the residual plot and my R squared is pretty high, then I would conclude that this is a reasonable fit, and therefore I would feel pretty good about making predictions using that line. Okay, and so speaking of making predictions, since this is a good model, how much would we predict a person who's 57 inches tall to weigh? And so what we can do here is 2 things. We can just use our equation. Remember, y hat, that's our prediction, that's our model, is equal to negative 52.5 plus 3.04x. So what I can do is I can just take that 57 inches, that's my height, and I can throw that in for x. And so if you plug that in for x, we would predict somebody, based off of this model, we would predict somebody that weighs or that's 57 inches tall, we would expect them to weigh about 120.7 pounds. We're not saying that that's definitely going to happen, but it's a prediction. All right, now something else that you guys can do is you can, if you have that equation in your calculator, and so stat calc 8, list 3, for me it's list 3 and list 4, and I put that into y1. So there's our equation. What you can do, instead of plugging in all those numbers that we just had up on our screen, since you have that in y1, what you can do is you can get the calculator to evaluate that equation at 57 inches. So how do we do that? We go to vars, y vars, pick that function, number 1, and we say evaluate this. So it's like saying f of 3 when you were back in algebra. Plug a 3 in for x. So we're going to say y1 of 57, and we can plug that in, and it gives us that 120.7 that we got a few minutes ago. Or I can do it even fancy. The more comfortable you feel with the calculator, the better. If I've got my line of best fit going through my scatter plot and I want to try to see what somebody that is 57 inches tall weighs, I can go second calc value, and I can plug in a 57, and see, it tells me that 120. All it's doing in the background is what we either do by hand, which is what was on the PowerPoint slide, or what the calculator just did a few seconds ago, evaluated this function y that's in y1, evaluated it at 57. And so you can go from there. And to wrap it up, finally, once we have that, so what does the regression line tell us about the heights and the weights in the sample? So after all that's said and done, we can make some pretty good predictions because our data is in fact linear. But again, I can't say that height causes weight, right? So what can I say at the very end is that the regression line tells us that there's a positive association between weight and height, a positive linear association between weight and height. I've verified it. I can use this model in order to make some good predictions and feel pretty good about it since my R squared value is pretty high. Okay, so that is chapter 8. And so hopefully you guys, finally, as a person's height increases, their weight tends to increase, right? Tends to increase. Don't say that it does, because then that's saying that one thing causes the other for sure. That's definitely going to happen. And so that is chapter 8. Hopefully you guys will practice their study problems. We're going to practice some more of this in class as well. So thanks for listening. See you guys on the next one.